Shall I start, ma'am? Just
Yes.
good afternoon to the distinguished dignitaries, respected organizers, eminent keynote speakers, researchers, academicians, scholars, and participants from across the globe. It's a great honor and privilege to be invited as the keynote speaker for this prestigious international conference. I sincerely thank the organizing committee for giving me this wonderful opportunity to share my thoughts with such an esteemed gathering. The beauty of mathematics lies not only in its certainty, but in its infinite capacity to reveal patterns hidden beneath complexity. The journey of mathematics has always been a journey towards deeper structure. Across centuries, mathematicians have sought to understand the invisible relationship connecting numbers, symmetries, transformations, and abstract systems. Among the many branches that have emerged from this pursuit, graph theory has evolved into one of the most dynamic and influential area of modern mathematical science. What began as a combinatorial curiosity has now become a universal language for describing networks, interactions, computations, biological systems, communication architectures, artificial intelligence, and complex adaptive structures. Within this remarkable discipline, sum graphs and integral sum graphs possess a special elegance. They embody the profound interaction between graph structures and additive arithmetic principles. At first glance, these graphs may appear to belong to a narrow segment of graph labeling theory. However, deeper investigations reveals that additive graph systems from a rich mathematical universal connecting combinatories, algebra, number theory, spectral analysis, probability theory, topology, optimization, and computational mathematics. Labeled graphs serve as mathematical models for a wide array of applications, including the internet domain, cryptography, data security. Ma'am, the next slides, move on the next slides, ma'am. Next one, okay. Next one, ma'am, it is okay, ma'am. Next one. Labeled graph servers, mathematical models for wide array of applications, including the internet domain, cryptography, coding theory, data security, communication networks, web page searching, and more. A straightforward, effective strategy for handling large graphs involves breaking down the graph and processing the subgraphs individually. The utilization of mathematical process in graph theory has established the initial steps towards replicating the interactions occurring among various components within a network. This exploration can be facilitated through the application of graph theory and the science of networks. A prevalent instance of a graph in everyday life is social media, where individuals or users are depicted as nodes, and the interrelationship between them are depicted as links. Modern mathematical research increasingly depends on algorithms, simulation system, symbolic computation, and experimental mathematics were developed to bridge pure mathematical reasoning with practical computational investigations. One of the defining features of this work is its extension towards generalized and interdisciplinary graph systems. Weighted graphs, directed additive system, hypergraph extension, fuzzy graph structure, dynamic graph evolution, and probabilistic models collectively illustrated the remarkable flexibility of additive graph theory in modeling modern complex systems. The interdisciplinary applications discuss and demonstrate the growing importance of graph theoretical structures across contemporary science and engineering. Cryptographic system, network coding, blockchain architectures, machine learning graphs, computational biology network, and social interaction systems all reveal how additive graphs frameworks can provide meaningful mathematical models for a real world phenomena. Then the concept of the structural oriented work for sum and integral sum graphs are presented for the following slides. It condenses for the following slides how mathematical foundations, conceptual evaluation, algebraic structures. One by one, I will explain. Then after that, the application oriented structures are there. The first one is sum and integral sum graph. A graph is classified as sum graph or natural sum graph when the vertices of G can be uniquely labeled with positive integers such as E equal to, next slide, mama, that is the definition for, okay. This is just listen here. A graph G is classified as a sum graph or natural sum, that is n, natural number, sum of numbers, that is n. It is only for giving sum graph for natural numbers only. We are putting the value of vertices and labeled one. When the vertices of G can be uniquely labeled with positive integers, that is n sum graph, such as the edges, the lines are E equal to UV. That is the line E is adjacent vertices. That is UV is the line in between the line have it. It is the condition is if the sum of the labels on the vertices U and V is also a label of G. An integer integral sum graph is just we allow an integers also. For n sum means positive integers and the all integers covered, it is called Z sum, that is the whole numbers including 0. That is the graphs demonstrated for sum graph and the integral sum graphs for the figure then given. The complete set graph corresponds to additive closure and subgroup structure. The sparse region corresponding to partial closure governed by modular arithmetic. The isolated vertices reflect some free behavior. Together, these phenomena illustrated the central thesis. That is, for some work, for this work is mainly focused on the central presentation of this work is the topology of a sum graph is a direct manifestation of an additive algebraic structure of its label set. This unified graphical interpretation provides a powerful and formal tool for analyzing some graphs across different algebraic systems. There are some graph over G. First one, so many graphs are there. First one is some graph over Z for a vertices 1, 2, 3, 4. Have a detailed manner. The graph is illustrated here, and the next one is Z 0, 1, 2, 3. How it is draw and how to measure, and the complete graph. Third one is the complete graph, vertices 0, 1, 2, 3, 4. How it is over field, algebraic system field, and the fourth one additive closure, and the fifth one homomorphic embedding, and the last one is additive dimension. That is the pathwise graph mentioning there. These are the resultant result, very important results for adapting the algebraic structured work and for interdisciplinary future work. It is mainly for how it is algebraic structure to adopt a label work, and how to it for in computer oriented or complex works, or the algebraic cryptograph, all the things we are utilizing, such as these graphs. The algebraic perfects the algebraic perspective on some graphs provides a unifying framework that connect graph theory with group theory. That is, group theory is mainly focused only for mathematical concept, and this one is connected with the graph. We are adopting ring theory and additive combinatories. By interplaying vertex labels as elements of algebraic structures, one gains access to powerful tool for analyzing graph properties, constructing examples, and providing structural results. The algebraic system from abelian groups to rings and field reflect increasing levels of structural richness, each imposing its own constraints on the corresponding sum graphs. Future directions include deeper classification results, algorithm recognition problem, and future exploration of connections with other algebraic graph constructions. And these are the, again, getting some graph structure extension for resultant graphs for categorize wise we are analyzing, and some samples graphs are occurring here. These framework demonstrate that some graph theory sits to the intersection of multiple mathematical disciplines. The structural theory of some graphs reveals a rich interplay between combinatorial constraints and additive structure. Necessary conditions such as minimal label constraints and degree bounds limit reliability, while constructive methods demonstrate sufficient in border setting. Trees and sparse graphs admit flexible representations, while cycle and dense graphics inherit limitations. And the algebra, and the next one is how we are adapting the analyze shows that some graphs and fundamental sparse object and algorithmic considerations highlight the complexity of recognition and construction. Advanced proof frameworks connect the theory to additive combinatorics, order theory, and linear algebra, establishing some graphs as a deeply interdisciplinary subject. Many problems remain remain open, particularly regarding type bounds, classification, and effective, efficient algorithms. The algorithm constructions and the computational complexity is getting first one algorithm we are construct and generate random labels, test additive relations, construct adjacency matrix, computation, compute invariance, store graph, metadata. And here the data set parameters are. Here, first one we known for n vertices must, and after that, edge density, what we are, how much we are putting there, and the graph feature includes, and the data storage, all the things are adapting for. Next slide, move on next slide. A data set row may contain, and first one graph ID G1 and G2. How many vertices are there? We put it 20 vertices and 45 edges for the condition is sum graph or integral sum graph. Chromatic number means and how many clicks, spectral radius, all the things we are getting, and stimulate framework is also using Mendel-Carlo simulation we are adopting here, and the how we are edge chromatic or vertex chromatic or the graph whole graph chromatic number we find out, and how the graph is decomposed or partition. The next slide for graph decomposition is getting for there, how to investigate method of decomposition of sum and integral sum graph, and how to a full graph, a large graph have it. We are decompose subgraphs. How it is one is the whole graph is a complete graph, and the edges are in the main graph, and then the edges are not. It is a complement. It is called anti-sum or anti-integral sum graph, and getting these using these techniques and the clustering or coloring. That is the nowadays it is very useful for all the network system works. Then graph coloring and chromatic properties we are investigate, and after that a generalized adjacency condition include the principles of mathematics, matrices and operation includes, and after that this is graph how it is. We are partially whole set whole. Suppose we imagine that full network. This is the third one is it is called mesh topology in network side or topology, and how it is decomposite and how it is packing. That is very important for sum and integral sum graph getting resultant. This is we are applied for interdisciplinary computational complex network analysis or coding or decoding, all the things we are adapting here. Um, and this is now one is graph coloring. Ma'am, move on the next slide. Have shows how it is we are. This one is line. We are edge wise. It is how we are coloring it. All the vertices are we are not coloring it. Only here we know the number of colorings. That is the minimal number of lines have one color. Now, what is the number? What is the upper bound? We are all we are analyzing the sum and integral sum graphs, and the coloring work or clustering work, getting click and all the things. It is very important. And this one is for vertex coloring. The previous one is edge coloring, and this one is for vertex coloring. We Suppose we are putting on Python code for getting our graph, and I will analyze and all the things for Google Colab, getting the all the graph models are getting, and the some graphs I am uh, present in the next slide for sum graph in cyclic group, random sum graph, and some threshold graph. All the things, how many vertex set, edge set, order, size, regularity, spectrum, and the second one is rules, expected number of edges, degree distribution, threshold for connectivity, and the last one, number of edges, asymptotally, properties, all the things I am getting from the coding for algorithm, utilizing and again adopting and using Google Colab, getting the uh, these types of network getting, and here we are using it as a it is very useful for interdisciplinary complex network system. Next one, next one for these are the sum graphs. Modern research focus on threshold functions, spectral asymptotes, graph limits, additive energy, and random integral labeling system. The subject remains a major research feature in modern discrete mathematics. And the next one is for dynamic weighted and generalized sun graphs. Using that also very important for interdisciplinary side, it is getting for so many results. For next slide have uh, weighted sun graph, edge set, edge weight, all the things, directed sum graph, that is the next one, multi-graph sum models, and the last one is hypergraph sum models, and the fifth one is fuzzy sum graphs. Fifth one is demonstrated for fuzzy sum graph, that is fuzzy adjacency matrix, how to get, and all the things explained for this one, and dynamic evolution model, here time dependent edge set, evolution rule examples are there, and the weighted degree, Laplacian weighted spectrum, all the things are there. Then parametric generalized sum graph, edge rule, special cases, connections between models, and all the details are hypergraph fuzzy with all the details are illustrated here. Just it is a very interesting for how we are adopting the complex model network. So very large networks getting the solution is a very interesting and simple manner getting these are. Dynamic weighted and generalized sum graph theory, extended classical additive graph theory. In multi-dimensional mathematical framework involves weighted interaction, directed flow, hypergraph structure, fuzzy uncertainty, dynamic evaluation, and parametric algebraic system are explained here. All the things detailed manner in the graph says what they are need, how it is implemented, all the things are there. Modern general sum graph theory forms an advanced interdisciplinary framework connecting combinatorics, probability theory, algebra, topology, optimization, dynamical systems, statistical mechanics, artificial intelligence, and mainly it is useful for network science. This subject continues to expand rapidly as new algebraic and computational models of future research. And the application of modern sciences and engineering. Here, using modern additive graph systems provide powerful mathematical framework for modeling distributed information and the complex adaptive system across contemporary science and engineering. The field continues to expand through interaction with artificial intelligence, quantum communication, systems biology, distributed computing, financial engineering, and probabilistic network science. And the next slide have some important network coding theory. First one is network coding theory, some graph of linear network coding, edges used for constructing and encoding subspace and combining flows. A rate rank of the flow is over the value is there. Then the second graph is cryptographic construction, sun graph for key structures, edges used by key agreement, hash function, and hard combinatorial problems. And the third one is additive combinatorials in communication system. And the fourth one is blockchain topology modeling, some graphs. And the fifth one is AI machine learning graph structure. And the sixth one is computational biology network model, molecular interaction model. And the seventh one is social and economic network analysis for using sum and integral sum graphs, error correcting codes from sum graphs. That is the matrices is that is a habit. And the fifth one is quantum communication, and ninth one is quantum communication. These are the previous slide is research emerging direction for the sum graph theory, additive combinatories, generalized graph system, all the things or interdisciplinary graph application requires methodological frameworks integrating analytic proof techniques, computational experimentation, and all the things is mainly focused on simulation method and algebraic construction and the remaining ones. First, to identify where the cap is, you identify. And then after that, the methodology we are putting here. The next one is getting for research cap identification and conjecture development strategy, and all the things we are utilizing here. The conclusion, and here the open problems are there, and some of uh, conjectures are there. These are unproved and unsolved works are there. This is very interesting for future direction of the research for interdisciplinary, mainly for coding and complex network models. We are mainly focus on this topic is very useful and unique one. Then the conclusion is open problems are so many problems are there and open conjectures are there. Every finite graph admits an integral additive representations. Random additive graph satisfies, and the spectral distribution of random additive graphs converge to a universal law, and all the things we are using very important. And the conclusion is mathematics is not merely the science of numbers and structures, it is the language through which the universe reveals hidden symmetry, order, and infinite possibilities. In the vast and ever expanding universe of mathematical science, graph theory has emerged as one of the most elegant and influential discipline of modern intellectual inquiry. From the earliest combinatorial abstractions to the spontaneous structures governing artificial intelligence, quantum systems, communication network, and computational biology, graph theory has transformed into a universal framework for understanding complexity itself. The future of graph theory will undoubtedly be shaped by interaction with artificial intelligence computations of within this grand mathematical architecture, sum graph and integral sum graph. This is the work mainly focused on sum and integral sum graph occupy a uniquely fascinating position where algebra, number theory, combinatorics, topology, probability, and computational coverage into a deeply interconnected domain of research. There is a feasible and appropriate approach in these conditions would involve dividing or partitioning or decomposing. That is the mainly focus to this work, the network into smaller segments that can be analyzed independently. The design where developed was utilized to identify network communities more effectively than the existing community deduction method could manage independently. Moreover, the majorities of communities remained intact and were not distributed by the partitioning of the network. In this evolving scientific landscape, generalized additive graph systems are likely to play an increasingly important role. It is my sincere hope that this work contributes meaningfully to the continuing evaluation and encourages researchers to pursue new ideas, deeper structures, and unexplored mathematical fortune. Mathematics is not the end of the discovery. It is the beginning of infinite questions waiting to be understood. May this work inspire curiosity, reduce imagination, and future mathematical innovations. The next two slides have some reference of the work. I conclude my section. Thank you very much for your patience listening.